G'day guys, today we're going to look at I2C interfacing with the bus side. I2C is a popular low-speed communications and bus protocol and interface used in embedded devices. The types of things that you might see I2C used for are sensors and also especially EEPROMs and non-volatile storage with low capacity. You might also have it used to communicate between chips or other reasons in embedded devices. In this particular photo I've shown here on the right, I've got a digital answering machine that has a bunch of test points exposed. I've soldered jumpers onto these test points. They're connected ground to ground, and I've also connected the remaining jumpers to the bus side. In this particular case here, I've directly connected to the I2C pinout on those female header pins, but if you don't know the pinout, you can certainly connect them directly to any of the GPIOs, and the bus side will do pinout discovery as well. So let's do that. We've started the bus side, our client. We can see that we've got some commands available to us, and let's just discover if there are in fact any I2C interfaces connected to those test points. And the reason that I think there might be is I've looked at the digital answering machine and I've identified an I2C EEPROM, and possibly that I2C EEPROM is connected to those test points, or that I2C bus is connected to those test points. So let's do I2C discover pinout, and we have in fact identified an I2C interface connected to our GPIOs. In this particular case, SDA is connected to 4 and SCL is connected to 7. And I'll explain what those mean in a second. The way that this I2C discovery works, it effectively brute forces the GPIOs with combinations of that 2-wire protocol, which I2C is, and brute forcing the clock line, SCL, and brute forcing the bidirectional data line, SDA. It is a 2-wire synchronous protocol, so we have identified that. Now I2C works as a master-slave bus topology, and each slave device has an address associated with it, and that's how the master communicates to it. Now, a particular chip might have more than one slave device associated with it, but let's see if we can discover the slave addresses associated with these with this particular I2C interface. And it has discovered one slave address with address 80 associated with this I2C interface. So let's just try dumping the EEPROM using our GPIOs that we've discovered, using our slave address, and we also need to put in the number of bytes used for addressing within the EEPROM. Some devices have 1 byte of addressing, some EEPROMs use 2 bytes for addressing. This particular EEPROM, by looking at the data sheet, uses 2 bytes. So let's also dump 64K of memory. We know that by looking at the data sheet. And now we're dumping the EEPROM. It does take a few seconds to run, but not too long. And there we successfully dumped our EEPROM. Let's exit out of the bus side client and look at our dump of. So this is a bit of data. We have an interesting line here, research in motion, Telstra 12750, which is actually the model of this particular digital answering machine. So it looks like we have dumped what looks to be a legitimate image of that EEPROM. Let's just run strings on it, and we can see we've got some information. Possibly this looks like some dialing codes. Our answering machine model, Apple, research in motion. So we have successfully dumped this EEPROM. And that's all I've got for this video today. If you like this content, we also offer training at InfoSec on interfacing with IoT devices, where you'll pull apart a bunch of things and interface with them using things like the bus side. Watch my other YouTube videos and subscribe. Hope you enjoyed this video, and I'll see you guys next time.